I dread to think how many A-level maths students lost their university place as a result of this question last summer. Don't let it happen to you this summer. Examiners said in their report, after marking all of the exams, that this question was a clear discriminator between the most secure and intermediate candidates, with many making little or no progress in Part A. In fact, the least confident candidates were just subbing in values randomly, and it scored no marks. In Part 2, many candidates did not fully appreciate what they were being asked to do, so lots of students there also scored 0 marks. Oh dear. So in Part 1, we're asked to show that this quadratic expression here is positive for all real values of k. This word all is really important. It means that we can't just substitute in some random examples and just show that those are positive. We need to use algebra to show that it works for all values of k. So how do we do this? Well, you might have your own ideas about how to do this. Maybe you can let me know in the chat. But my preferred method is to use completing the square. How do we complete the square for this quadratic? Well, let's focus in on this part. How could we write that as a completed square? Well, I know that it's going to come from k minus 2 multiplied by k minus 2, because that's going to give me the minus 4k when I expand the brackets. But it would also give me a plus 4. So I need a plus 4. Why don't I write a plus 4? But there wasn't a plus 4, so I'm going to have to cancel that out by writing a minus 4 here. So all I've done is I've added 4 and subtracted 4. Really, I've done nothing, right? Plus 0. Why have I done this? Well, this part you should recognise as k minus 2 all squared. That's the completed square part. If we combine the minus 4 and the plus 5 together, we get plus 1. How does this help us? Remember what we're trying to do. We're trying to show that this is positive for all real values of k. Why is this positive? Well, this is a squared term. So it can never be negative. It can never be less than 0. It could be 0 if k equaled 2. Yeah, that's true. But it could never be less than 0. So this part we can say is greater or equal to 0 plus 1 with this 1 here. 0 plus 1 is 1, and 1 is greater than 0. So it's strictly positive for all real values of k. Part 2. A student was asked to prove by contradiction that there are no positive integers x and y such that this multiplied by this gives us 28. The start of the student's proof is shown below here. They've assumed, for contradiction, that positive integers x and y do exist. Remember, we're trying to show that there are no positive integers. So they've assumed the contrary to that they do exist, such that this is true. And they've thought about, well, here we've got an integer, right? If x and y are integers, well, 3x is an integer, a whole number. 2y is an integer too. And if you add two whole numbers together, you get a whole number. Same thing here, right? In fact, this is going to be an integer. Take away an integer, that's also going to be an integer. Notice, by the way, also, if x is a positive integer, and same for y, then 3x will be positive, 2y will be positive. So when we add these together here, we're actually getting a positive integer. So this bracket is positive, and it's multiplying with another integer to get something that's positive. Positive multiplied by what gives us positive? Well, this has got to be positive. That's really useful because it means we don't have to consider the cases where this and this might both be negative, right? Negative times negative could give us positive. But because we know this is positive, we know that this too must also be positive. So we don't need to consider any of those negative cases. Okay, so we've got integer times integer, giving us 28. What are the possibilities? Well, they've given us one here, 14 and 2. Yeah, this could be 14, this could be 2. If we solve these simultaneous equations, which you're allowed to use using your calculator, we get this. But these are fractions, not integers. And we assumed that there were positive integers, x and y, that exists that did this. So that's a contradiction. But this isn't the only case. We need to show the calculations and the statements needed to complete the proof. So let's just note that as x and y are both integers, then this and this are both integers too. So we don't need to consider any fractions or decimals, anything like that. Also notice that this part is positive, as we discussed before. So this is going to be positive too. So we only need to consider products of positive integers. So what could we have? Well, 28 we can get from multiplying 28 by 1, 7 by 4, 4 by 7, 2 by 14, or 1 by 28. So there we go, we've got 5 other cases there. And in every case, if you solve these using your calculator, which you're allowed to do, you can just write down the answers, you can see that we have a problem. Here and here, we have fractions, not integers, not whole numbers. Here, we've got a fraction, not an integer. And also, if you solve for y, in fact, you get a negative number. It's not positive. It's similarly the case here that we end up with a negative value for y, not a positive integer. And here, finally, we have both problems, not an integer, not positive. So in every single case, we have a contradiction. Hence, the original statement, this statement here, must be true. It's proved.